Yeah, I was talking about the grandma once. I have a family member that told me that they don't have electricity.
That means you get to wash the car?
Yeah.
Okay, that's fine. That's fine.
So if I did the homework, what do I do? Do I hand it in or do I send it by email?
You can give it to me. And remind me to give you back your test too. I'm sorry I didn't. The reason I wasn't going to write you right away because I had planned to finish it to do them that night. And I wasn't sure if I was going to do them. I apologize. I should have at least written in so well. But the grades are online. Okay. Anyway. Today we're going to talk about risk and uncertainty. And we're going to use a lot of the same tools that we used in game theory, but in a different manner. We use the decision trees, but they're going to be used a little different. It's not in a strategic manner. It's just in a manner to decide where what we should do when we face uncertainty. So the objective is to explain how managers should make strategic decisions when faced with incomplete or imperfect information. Okay. Okay. We're going to use expected value. It's just math. And expected value ends up being an average. Usually a weighted average. Decision trees are going to be a lot like the decision trees we used in game theory. Techniques to reduce uncertainty and expected utility. That'll tell us our attitude towards risk. So here's the definitions. Risk is simply the hazard of chance of loss. And probability, get a statistics class, you know this already. The likelihood or chance that something will happen. Okay. So what is frequency? Definition of probability. Events, limits of frequency in a large number of trials. It's basically just how many occurrences you get of each possible outcome. So the probability of events is simply the number of times the event occurs divided by the number of trials you have. So in terms of our slideshow there, the little r is the number of times that a certain event occurs, we call it A. And big R is the total number of trials that you try. So little r over big R gives you the probability. Fairly straightforward. A subjective definition of probability is the degree of a manager's confidence or belief that an event will occur. This is, of course, subjective probability. In other words, what do I think the probability is? Okay, some of the rules of probability. Probabilities have to be between 0 and 1. Given a list of mutually exclusive, collectively exhaustive events, events that cannot occur in a given situation, the sum of all the probabilities has to equal 1. So probability distribution, a table that lists all the possible outcomes and assigns probabilities to each occurrence. Here we have a definition of expected profit. So under each occurrence in, or what we call in economic states of nature, you'll have a certain profit level. You multiply those by the probability of that event occurring, sum them all up, and that would be your expected profit. In essence, it's a weighted average of profits under different scenarios. Under different probabilities. So here's a table. There's a 50% chance that things will turn out good, and you'll earn $800,000. There's a 50% chance that things will go bad, and you lose $600,000. So if I multiply 800,000 by 0.5, I get 400,000. I do the same thing for negative 600, I get negative 300,000. I add those up, and that gives me my expected profit. In this case, it's $100,000. Okay. The payoff from not increasing price, in this case, is $200,000. So $200,000 is greater than $100,000. So for most people, the optimal strategy in this case would be not to increase price. We're going to see a while. If you're, in this case, would have to be extremely risk-seeking. You might want to raise price simply because you're hoping this will happen, and you're hoping you're making $800,000 in profit instead of $200,000, instead of the expected payoff of $100,000. But that's only if you're risk-seeking. In other words, you really like to gamble. Okay. The next thing we're going to look at is a decision tree. It's simply a diagram that helps managers visualize their strategic future. So it looks a lot like we had those trees that we had in game theory. But here, right, there are two choices, and we don't have to worry about what somebody else does. It's just we have to assign probability to different occurrences. In this case, right, if we increase price, there's a 50% chance that we'll have $800,000 in profit, and 50% chance that we'll lose $600,000 in profit. And of course, if we don't increase price, we get $200,000. That's a simple decision tree. The next thing I want to talk about is how much perfect information is worth. In other words, if I knew for sure that if I increase price, it would be successful, or I knew for sure it would be unsuccessful, how much is that worth to me? Okay. Well, if I increase in expected profits from completely accurate information, right? Given our example, right? If I had perfect information, the company would increase the price if the campaign was successful and would not increase it if the campaign was not. We saw what, so if I knew it was going to be successful, right, I'd get 800,000, right? If I knew it wasn't going to be successful, I would not increase price and I'd get 200,000. I add those up, that's $1 million, 800,000 and 200,000. Divide that by 2, 50-50, or multiply each one by 0.5, and that gives me an expected value of perfect information of 500,000 minus the 200,000 that I'd get if I didn't. And so the expected value of perfect information is 300,000.
That's just an example, right? That's not a rule or.
This is just if I can.
I mean the 800,000 and for the 200,000, that's not a rule. Not a rule
Like a given formula.
a given formula.
I don't know how to answer that question. Okay, the 800,000, that comes if I know I'll be successful, that's what I'm going to do. If I have perfect information, and I knew if I knew I was going to be successful, I didn't think about that. That's it. So all the good events, like if this had more than 2, I would take all the good events, right? And if I knew one of those good events was going to happen, well, I'd just throw that on. The 200,000 is if I know things are going to go bad, I'm not going to increase price. So I get the 200,000, right? And of course, then, divide that by 2. Our 2 options is 500,000. I subtract off what I was going to do normally without the perfect information, the 200,000, and it gives me how much perfect information would be worth to me. Now, it's kind of silly because we're never going to have perfect information.
But my question is, from where is that 800,000?
So today,
Yeah,
That's the actual number.
that's what, that's.
Oh, okay. Slow me down. Slow me down because I think I'm going too fast then. Okay, here.
Okay.
Here we have Slow me down, ask questions. I'm going too fast. Okay, so at 800,000 here, if things go well, I make 800,000.
Yeah, 'cause I was like, is that a given every time I have to write 800,000?
No. I misunderstood the question. When you said formula, I expected the actual formula where you plug in the numbers that you're given. Here we're given this number. And it's also, we use the same numbers on our decision tree right here. 800,000 up here, and then negative 600 down here. So, and this is just if I have perfect information. If I knew for sure things were going to go good, I'd raise the price. If I knew they weren't going to go good, I wouldn't raise the price, and I'd just stick with the 200,000.
But when you say raise the price, do I put the price?
Yeah. Okay. Coming back up here. Here's the Joe's Corporation is considering the decision involving pricing and advertising, right? So if they raise price, they choose to raise the price, right?
Whatever.
And this is very simple because obviously it's not going to be discrete, it's going to be continuous. But if they raise the price, there's a 50% chance that things will go well and they make 800,000. 50% chance things will go bad, they lose 600,000. So it's just part of the example it's given. And of course, this is if I had perfect information, right? That what it would be worth to me. If somebody was able to sell me a genie that was going to tell me exactly what happened in the future, right? That's what it would be worth to me, 300,000.
So that's eliminating the possibility, the probability factor, right?
Yeah, in other words, we're going from uncertainty to certainty. Yes.
Just assume that's the case scenario, right?
No, because you know, the genie tells you, you raise
Right,
price.
Best case scenario, really only scenario.
Yeah, in that case, and that's when you raise price. If I know things are going to go good for sure, because the genie told me, then I raise price. If I know things are going to go bad for sure because the genie told me, then I won't raise price. So obviously, as I was telling you, there's no genies in the world, but it does give you an idea, an idea of having. Ooh, window shook. Okay. Well, this is flimsy, so.
I think we're running out of electricity.
I guess, I think our question earlier would be, is there a formula for expected profit when you have perfect profit? Is it like?
The answer is no, because you know exactly what your profit's going to be.
So you know your profit by adding the 800,000, which would be the best case scenario in the tree plus the payoff. And divide that by 2, right? I think that's what you would find at.
Yeah, no. In other words, if I know it's going to be good, I get 800,000.
Oh,
I know that. Huh?
that's a general rule.
No, I mean that's where this.
The 800,000 is not a general, not the number, not the number. Things go good. I know exactly what happens. That's what I get.
Because we have 2 scenarios: 800,000 or negative 600,000.
Yes.
So basically, the 800,000 we present the best case scenario.
Yes.
I know we're not.
Before with uncertainty, best case scenario.
Right. So I guess I think what she's looking for is a variable to substitute that in the formula. The expected profit would be equal to.
Yeah, what would be the formula under that?
Okay.
But I see what you're saying. The there isn't really one. Right?
Well, we can make one up. We can divide one.
Básicamente el expected profit es sumar. O sea, si todos sabes que el mejor, lo que sería el mejor case si cambiara el precio, igual sería lo que están ganando si no le cambias el precio. Lo divides entre dos porque pues, la probabilidad de... Claro, hay dos opciones, you drill well or you don't drill well. Pues entonces yéndose por eso. Camino perfecto. You drill well, sacando 800. No, I'm sorry, I'm looking at another.
XP, right? And that's, I'm assuming two outcomes. Obviously, there's going to be a lot more outcomes. But here,
Right, exactly.
right? So I can do this, the XV, right? So I'll call it probability. Then times XG, so the probability. XP, right? This scenario, that scenario, and the fixed
Can you
probability.
make it bigger, please?
Huh?
Can you make it bigger?
Oh, yeah, sorry. I write the probability, so I understand. Actually, hold on. I don't even know if Julian's looking right now.
I'm thinking, you must be what are they talking about?
I don't know if you see this. Okay. So I have XG, XB. I have the probability, I'm going to say, of good things happening. When I raise the price, the probability of bad things happening. So XG times the probability of good things happening when I raise the price plus the probability of bad things happening times the payoff of bad things happen, right, gives me my expected cost. That's now for the value of perfect information, right? Well, if I have perfect information, I'm only going to raise price if I know this is happening, right? So basically, at that point, this is either 1 or this is 1, right? If this is 1,
But the first case scenario, but
yeah, it's the best case scenario in this case where we only have two.
yeah.
So if this equals 1, right, then my payoff is XG. Our example, 800,000, right? If the probability G equals 0, then my payoff, if I raise price, right, is XB. Okay. But this, I'm not going to do because it would be dumb. I'm not going to raise price if I know I'm going to lose $600,000. If I know for sure that I'm going to lose $600,000, there's no way I'm going to raise price. So in this case, I won't raise price, right? And I'm sorry.
If you're gonna lose $600,000, you just close the business.
Well, in this case, it's not about closing or continuing. It's about raising price or not. Go ahead. The $200,000 is just the assumption from the model that says that if you keep prices the same, your profits are going to be $200,000. And he assumes he knows that with certainty somehow. So in this case, right, since I'm going to call it YN, Y nothing, right? I don't do anything. Oops, since XP is less than YN not doing nothing, then I do YN. So YN plus XG, right? That's in our example, 800,000 plus 200. Go ahead.
That XP is less than YN.
YN is do nothing, and YN do nothing in this case gives us 200,000 in our example. So for our case, right, the value of perfect information is going to be xg plus yn divided by 2 because the two possible outcomes, right? Minus yn.
So it's a good scenario plus the do nothing scenario divided by 2 minus the do nothing scenario.
Exactly. Does that make sense? Vilma?
That way, another one.
Julian, do you see that?
Yeah, I'm here. The thing is, I'm charging the phone, so I'm just seeing it from the
Do you
computer.
see it normally or do you see it backwards?
I see it pretty well.
I mean, but you can read it, it's not backwards.
No, it's normal. Yeah.
Okay. Because for us, it's backwards. See, that's what I was saying the other day when I was telling you that it's backwards.
XC was the problem, XC was the good thing, right?
XG is a good state, XB is payoff in the bad state, and YN is do nothing. I should have thought of the great
So
over.
that is best case scenario plus do nothing divided by 2
Minus do nothing.
minus do nothing. And why do nothing? Why do you add do nothing and then discuss nothing?
Because if this is true,
Yeah.
right, then I'm going to go with do nothing because I'm not going to lose 600. I'd rather take the 200,000. Right? So if I know for sure that, by the way, this is saying the PRG is equal to 0 is the same thing as saying PRB is equal to 1. Right? In other words, the probability of the bad state is equal to 1, it's 100%. Sure. Are we good, Mike? You wanna? We can go through. We can do a little more on this if you like.
I still don't understand what do nothing.
The do nothing is you get 200,000 if you don't raise price. In our example.
But then, still my question, the adding and then
I'm sorry.
the do nothing. I
Okay.
don't get what you
Because what we're talking about is the value of knowing with certainty. Right? And that's the thing. If not, I can just take 800,000 minus 200,000. Right? That'll give me 600,000. But that's not quite the value because that's not what it's worth to me because there's a possibility that knowing for sure is this. That the probability of the good state is 0 and the probability of the bad state is 1. Right? In other words, I'm not 100% sure that if just because I know everything that it's going to be good for me. It might be bad. So the value of knowing for sure, right? That's why I take this. It's the bad state. This would be the bad state. But in the bad state, I'm not going to do that. I'm going to do nothing in the bad state. So that's why I have the y in here.
And that is best case scenario. That's not the equation.
The XG is the best case scenario. This is expected value of perfect information.
But the whole equation is xg plus yn divided by 2.
Expected value of perfect information.
Oh, it's just wanting to know that.
Yeah, if you could sell me that genie that tells me this one thing, how much is it worth to me?
So that is the genie, that equation.
Huh?
That equation would be equal to the genie.
That's how much the genie's worth to me, yes.
Okay.
Okay.
Yeah.
And it's, well, it's right there. That's how much the genie is worth to me. Okay. Here we have another decision tree, and this is about Genco Exploration. They're an oil firm or an oil exploration firm, and they look for oil. And they found all the evidence that there might be oil in a certain spot. And there's a 40% probability that there'll be oil in that spot. How much oil, they don't know, if there is oil. So it has two choices. They can drill the well and see if oil comes out, or they cannot drill the well, right? And in this case, if they don't drill the well, their profits are $0. If they drill the well, there's a 60% chance that there's not going to be any oil, and they have to eat the cost of drilling the well, which is $90,000. There's a 15% chance that there will be oil, but it won't be that much oil.
We have 56,000 guaranteed profit just by choosing to drill. That 56.
That is the expected profit.
Oh, taking into account all the.
Yeah. In other words, get that. Julian's right. 0.6 times negative 90 plus 0.15 times 100 plus 0.15 times 300,000 plus 0.10 times 500. Huh? Expected value is always an average, usually a weighted average. Yes. So, like I said, going through that, there's a 15% chance that the well will produce 10,000 barrels, and that'll give you $100,000 of profit. There's a 15% chance that it'll produce 20,000 barrels, and that'll give the company a $300,000 profit, and a 10% chance that it'll give you 30,000 barrels, and that would give you $500,000 profit. I do the weighted average of the probabilities times the payoffs in each case, and that gives me an expected payout or an expected profit from drilling of 56,000. Now, we're going to see later on that if I'm risk neutral, in this case, I'm going to drill, right? It may be that somebody who is risk averse, and we'll talk about this a little later, may decide that 56,000 isn't enough for the risk, right? And he might decide just to take the zero because he doesn't want to risk the negative 90,000. Questions? Clear, Maribel? I mean, Bloody Mark, sorry.
So you have to multiply the 150 times the 90,000, the 150 times the
Yes.
100,000, and then after all of that, those results will give you the weighted average.
That is the weighted average. Yeah. See if I remember all of this. So if they drill, right? If they don't drill, it's zero. If they drill, right? The expected profit is going to be 0.6, 60% that there's no oil, right? Times negative 90,000. If they drill and there is oil, but there's not a lot, 10,000 barrels, there's a 15% probability of that. And in that case, if I remember correctly, they get $100,000.
Actually, it was 100,000 barrels.
No, 10,000 barrels.
10,000 barrels?
Yeah. It was 10,000, 20, and 30,000. And if it's a little better and gives you 20,000, right? Well, there's a 15% probability of that, and you'll make 300,000. And finally, we'll check this now in a second.
A 10% chance.
There's a 10% chance that there's 30,000 barrels, and in that case, you make $500,000 or 500,000. And in that case, you make 56K. Did I write that big enough, Julian? Can you see that?
Yes.
Okay. All right, let me go back to. Make more sense, Raymond? Yeah. Okay. Okay. Yeah. So it's 10,000 barrels, 20,000, and 30,000 barrels. Okay. I told you we were going to talk about attitudes towards risk, and that's where we're going to start now. Here's an example. I have a small business, and they're offered the following choices. They can either accept $200,000, and that would be certain profit, or they can enter a more risky endeavor, where there's a 50% chance that they'll make $4,100,000, and there's a 50% chance that they'll lose $60,000. Right? So that's 0.5 times 4.1 million times 0.5 minus 60K. And that gives us an expected profit from this gamble of 2,000,020. Okay. So certain profit is 2 million. With the gamble, the expected value of the gamble is 20,000 more. You guys take the gamble?
I don't think it's worth it. 20,000 extra when I could be using 60,000. Like a 25%.
Everybody agree? Okay. You guys are risk averse. If you were risk neutral or risk seeking, you would definitely take the gamble. So if the business is risk averse, it's likely to take the certain profit, like you guys are. I'm sorry?
That's also true.
Actually, that's a good point. And risk aversion, there are models where risk aversion depends on wealth.
Good side versus the bad side.
I'm sorry?
Considering
The good side versus the bad, yeah. But we're going to see that we can apply this to utility functions. These utility functions are a little different than the ones we were working with at the beginning of the semester, in that we don't worry, our utility is not derived from consumption per se, but it's actually derived from our wealth. So in this case, we have a utility function used to identify the optimal strategy for managers conditional on their attitude towards risk. But instead of doing consumption of different goods like we did before, now we're doing it with wealth. Right? And more wealth is better in general if there's no risk. So we want to construct a utility function. Our expected utility is going to be very similar to our expected profit, except we add up the utilities and not the profits. So each profit will give us a certain amount of utility, and instead of adding up the profits, we add up the utility. So expected utility is the sum of utility of each outcome times the probability of the outcome's occurrence. Go ahead.
Do I use imaginary units details, or
In this class you are going to use the imaginary utils, yes.
I'm not there in expected utility.
Yeah, perfect. That's exactly what we're going to do in this class. We're going to assume that we can measure utils, and we're going to have a function that tells you for each dollar of wealth you get, how much more utility you get.
And how do I get those numbers? I mean, how can I make sure that
the formula will be given,
okay.
And then you just have to calculate it.
Okay.
All right. Go ahead. K as in thousand. Sorry, I write horribly. I understand. Okay. Okay. So here we're going to construct a utility function using two assumptions, right? I'm going to arbitrarily assign utility levels to two payoffs, with the highest payoff set to a higher level of utility and a certain profit of 200,000. So for this corporation that we were talking about, right, the utility of striking it well and getting that 300,000 barrels, right, gives the company a utility of 50. But if things go bad, and they lose 90,000, their utility is 0. And that's just by assumption. So the next thing I want to do is ask the person involved, the one making the decision, what probability would make them indifferent between, say, 100 and the following gamble. My utility for the good thing, I get 50, and my utility for the bad state, I get 0, ignoring the other two states that we use. So that's the probability times 50 plus 1 minus the probability times 0. Now that would be their expected value if those were the only two things happening. Suppose the decision maker says if the probability is 0.4, right? Or P is 0.4. In other words, instead of having a 10% probability of 500,000, you get a 40% probability of 500,000. That I'd be indifferent between that and a certain profit of $2 million. In that case, right, the expected utility is 0.4 times 50 plus 0.6 times 0, or 0.4 times 50 is 20. And of course, anything you multiply by 0 is 0. So I have an expected utility, right, of 20. And by the way, I said $2 million, I meant $100,000. Right? So continuing this method, I got it for the extremes. Now I can do it for the other two scenarios where I have 100,000, I'm sorry, when I have 10,000 barrels and 20,000 barrels. Okay. And that allowed me a derivation of utility with possible payoffs, or a utility function or a curve.
And when you write that gamble, the following gamble number 2, that is the formula. That's just an example.
No, that's an example because it says utility of the 500,000 is 50. You also want to add the probability of it not happening, which is 1 minus P.
Does that make sense? Basically, what this is saying, I'm asking you, right? There's two things that can happen. Right? If I said you lose 90,000 or you gain 500,000, what probability of gaining the 500,000 is giving you utility of 50? Huh? No, this is the payoff of utility. And you lose what you utility, how much happiness it will give you. This is what happened. In this case, it's 0.4. For you, it might be higher, it might be lower, right? And so if it's 0.4, right, that'll make me different from doing this or taking $100,000. You give me $100,000 for I go to well or not. Basically, I take the gamble, or you give me 100,000. What would make? Or what? Actually, no. What will make me different? What's the probability of me getting the 500,000, which gives me utility of 50, right? What's the probability of making a difference between those two things? And in this case, the book takes it out of the air and says it's 0.4. 40% probability of me striking oil well with $500,000 or 30,000 barrels. And once you do it for that one scenario, and then you can do it for the other scenarios that we had, and those where they strike 10,000 and they strike 20,000, and then you can get a curve that shows you how your utility looks like. Okay. And in this case, right, we have the two middle ones. Right, I know what this was 100,000. 0 the product, the division, $0, not really, gives you 10, and of course losing the 90,000 gives you 0. Over here on the different, right, with the utility of 40, 200,000, and finally 100,000. So that's basically my utility function, right, or curve of my utility function. And you notice that this is slightly concave. That would indicate that this person is risk averse, which we'll talk about soon. Okay. So here, risk averters, when managers prefer a choice with a more certain outcome to one with a less certain outcome, when confronted with gambles offering equal expected wealth. The utility function has a diminishing marginal utility. In the example I gave a couple slides ago, where I had a choice of $2 million or a gamble that gave you an expected profit of exactly, you guys all chose the 2 million with certainty. That makes you guys risk averse because you preferred that certain outcome to the one with
On the expected payout also wasn't that much higher.
no, it wasn't. But it still makes you risk averse. Well, let's say that the expected payoff wasn't 2,020,000, but rather just 2 million, where you had the choice of 2 million with certainty or 2 million in the gamble. But the gamble, right, has the possibility of a $4 million payoff, $4,100,000. If you're indifferent between those two things,
And you would go for the one where you have any.
for 2 million certainty or 2 million in the gamble, if you're indifferent, you're known as risk neutral. You don't care about the risk. You just,
So only the really wealthy people.
it's a little more than that. You probably know poor people who like to go to the casino and throw the dice or whatever it might be. Okay. The next thing I want to talk about are risk lovers. When a manager prefers a gamble with a less certain outcome to one with a more certain outcome when confronted with gamblers offering equal expected wealth. In other words, somebody who's risk loving, just the thought of that $4 million, right? Even though 50% is enough for them to take the gamble because they like the risk. They like the chance of getting that high outcome, that high. And in this case, if you're risk loving, your utility function has increasing marginal utility. When I say increasing marginal utility, it's with respect to wealth. Right? And finally, risk neutral. In that case, it's a straight line. I don't care. I can get $2 million for certain or $2 million a gamble. I really don't care, as long as they have the same expected outcome. Okay. And in that case, it's linear and constant. Okay. So this is a graph of somebody who's risk averse, right? The graph's kind of a little complicated. I made it basically for another class. But at this point, this person has wealth of W star. Now he can enter a gamble that'll give him H with a certain probability, or he loses H with a certain probability.
It kind of looks like a normal distribution and kind of looks like a bell curve.
No, no, because this doesn't go down. It's concave, but it increases at a decreasing rate, but it never actually comes. Well, I guess it could, but it's not going to be symmetric. And it's not a distribution. It's not a probability distribution. You have wealth here and utility there. So in this case, his wealth, right, from not taking the gamble, and this would be his utility from taking the gamble. Even though they have the same expected wealth, right, he's just reversed here, that concave, right, he has decreasing marginal utility with respect to wealth. And therefore, he prefers a certain outcome to the risky outcome, even though there's a chance of you getting this H of it. Or he can take a bigger gamble, where he either wins 2H or loses 2H. And again, his utility is even lower with the gamble in this case because of this. He has that concave utility function. Questions? Okay. The next example is somebody who's risk loving. This guy has a convex utility, increasing marginal utility as well. Right? He prefers the gamble. So if he has that gamble, he either wins 2H or loses 2H, right? Or the certainty, he does the star. Well, in this case, right, is utility is higher, right, for taking the gamble than if he didn't take the gamble. So he has more utility. That makes him risk loving. Now notice that at this utility level, for him to have the same level of utility, is that my computer? Or my phone? Oh, I'm sorry. Sorry, guys. Yeah, it just said, flood advisory. Now I don't know how to get to it. Flat flush warning this area till 10 p.m. Atlantic Standard Time. Avoid flood areas. Check local media. Okay, so for him, right, to avoid the gamble and take this with certainty, you'd actually have to pay him that difference. Take it all the way to the utility function, come down, call it the rebar. I'd have to pay him that difference to get him to avoid the gamble and just take his loss with certainty. That make sense? Very much. This is mainly for you guys to get a better understanding. If it doesn't help, then just look at what the book says, right? And I'll give you the graph of the book in a while. And finally, we have somebody who's risk neutral. He doesn't really care if he takes a gamble or not. He's indifferent. That doesn't sound logical to us because, I mean, well, you should, I mean, why would you take the gamble? But remember, there's the possibility of the good outcome. And here, this is from the book, right? I have that first graph is risk averse. The second graph is a risk seeker or risk lover. And the last one, the straight line, is a person who's risk neutral. Questions? Okay. We did this the absolutely first day of class. I told you guys how to derive a standard deviation. And here we're taking the standard deviation of profits, right? Here I have the probability of each occurrence times the profit on each occurrence minus the expected profit. And this is just the average, the weighted average. Squared. I square it, and then I take the square root. When I square it, I get what? Without taking the square root. Just squaring it. What do I get?
You multiply by itself.
Yes. What's it called? About. Huh? No, 85 squared, but that's not what I'm talking about. What's okay? If this is the standard deviation, sigma. What's sigma squared?
Okay, sigma squared. That was variance.
This is, in other words, if I didn't go to the 0.5 and I just had to square, that's the variance. Then the 0.5 gives me the standard deviation. So the square root of the variance is the standard deviation. That's all that is. Right? So I might ask you someday, on the final, for instance, to calculate the standard deviation. The coefficient of variation is simply, right, the standard deviation of a risky project, or basically anything, the standard deviation over the expected profit. That's the coefficient of variation. That basically tells you how much the the project varies compared to what the expected value is. Right? And that's exactly what it is, because standard deviation is how much it varies. Right? So measure of how much it varies divided by the expected profit. Questions? Okay. I just wanted to make sure I was broadcasting today. I did a whole class just showing the camera on me instead of the instead of the. Okay, here I have two projects, panel A and panel B. And the profits and the distribution, right? So panel A, there's a 5% chance of losing 2 million, a 10% chance of losing 1 million, a 20% chance of zero profits, 25% chance of 1 million, a 20% chance of 2 million, a 10% chance of 3 million, and a 5% chance of 4 million, and 5% chance of 5 million. Here we have this graph. There's a 10% chance of losing 1 million, a 25% chance of zero profit, a 30% chance of 1 million, 25% chance of 2 million, and a 10% chance of 3 million. Okay. Which of those two projects or panels has a higher standard deviation? Which is riskier? Why is that?
Because it has a wider dispersion.
Wider dispersion. That's another way of saying it has a higher variance or a higher standard deviation. Yes. It has more risk. So this one has less risk. Okay. Questions? So basically, the higher standard deviation in general, the higher the risk for a project. And same thing with variance, since variance is simply the square of the standard deviation. Okay. Certainty equivalent approach. It's when a manager is indifferent between a certain payoff and a gamble. This is very similar to what we did a while ago, right? When we started when we asked the person what probability would make them indifferent between the two outcomes, right? The certain equivalence can identify whether the manager is risk averse, risk loving, or risk seeking. Okay. If the certainty equivalence is less than the expected value, then the decision maker is risk averse. If the certainty equivalence is equal to expected value, he's risk neutral. And of course, if the certainty equivalence is greater than the expected value, then the decision maker is risk loving. Okay. Questions? Okay. So the present value of future profits which the manager seeks to maximize can be adjusted for risk by using the certain equivalent profit in place of expected profit. Okay. So when we look at the indifference curves, is the manager's indifference curve and expected profit risk, with the expected value on the horizontal axis, the horizontal intercept of an indifference curve is the certainty equivalent of the risky payoff represented by the curve. If a decision maker is risk neutral, of course the curve is going to be vertical. Okay. So here we have the curve. Okay. And here I have risk. This is the coefficient of determination. Divided by the expected profit. And here we have the expected worth, the expected profit in $100,000. So here, right, this person, right, is risk averse because he has a concave utility function, right? And the risk coefficient, right, at 200,000 is 3.1. I'm sorry, the coefficient of determination is 3.1 at 200,000 and 0 at 100,000. So if I expect 200,000, right, I'm willing, right, to take risk as measured by the coefficient of determination of 3.1. Okay. Here's a mathematical example. Suppose I have a manager that has $900 billion in Puerto Rican government bonds. I knew that. Okay. And there's a 25% chance that the value of those bonds will fall all the way to 400 million. And there's a 75% chance that the bonds will remain with their value, with their face value. Okay. So the expected value of this is pretty straightforward. 0.25 times 400,000 plus 0.75 times 900,000 gives me an expected value of those bonds of $775 million. That's the expected value of these bonds. How much, right, would you pay me, or how much would you have to offer me to sell it to you? Well, let's suppose the manager has the following utility function. Basically, the wealth, which is in dollars, basically the bonds, it's a square root of the wealth, or W2.5. Right? So in this case, the manager's expected utility is going to be 0.25 times 400,000. 2.5 or square root of 400,000 plus 0.75 times the square root of 900. I'm sorry, 900 million, not thousand. Okay. And that gives me an expected utility for holding the bonds of 27.5. If I know my expected utility, I can take the inverse of that, and if I know it in terms of wealth, basically what I can do is I can take that utility of 27.5 I can take the utility of 27.5 0.5 equals 27.5. Did that feel much? So I have to solve for W, right? So I square both sides, and get W is equal to 27.5 squared, and 756. Okay. And it is 756 and 25. So, right, that's how much I would have to offer him for that bond, for those bonds, to make him indifferent between selling to me and keeping the bond. Right? So I offer him a little more, he'd take it. If I offer him less, he would not. And I find that he'd be indifferent between taking it or not. So the certainty equivalent should be the manager's reservation price for selling the bond at a discount. And this kind of the discount to the face value, where the face value is 900,000. Okay. So we see that he's willing to accept less than the face value. How much would he be willing to pay for somebody who would insure the bonds? In other words, they pay the difference between what the bond pays you and the face value. So if the bondholder pays you face value, the insurance company gives you nothing. If he gives you 400,000, you make up the difference, or at least part of the difference, depending on how the how the policy is struck up, if you have a deductible or not. So LBI provides full coverage of loss and is risk neutral. In this case, the insurance company is risk neutral. LBI's expected payoff is $125 million, so that the minimum price for the policy would be $125 million. The most that the is worth to the buyer is the difference between the face value, $900 million, and the certainty equivalence of $756 million and 0.25 million, sorry. That difference is $143.75 million. So the risk premium is the difference between LBI's reservation price, which is $125, and the maximum that the buyer is going to pay, which is 143.75 or 18.75 million. That's the risk premium, right? Or the amount above what the person is willing to pay that they're charging them for the insurance. Okay. Now, since LBI is risk neutral, why is their expected payout 125 million? Let me go back. Remember, LBI pays the person the difference between what the bond pays them and the face value. So if the bond issuer pays the full face value, the insurance pays nothing. So why is the expected payout 125 million?
Whoever issues the bond pays X amount, and the difference between X amount and whatever else is
125.
125.
But there's a 25% chance, right, that he'll excuse me, that the bond issuer will only pay 100 million, excuse me, and that difference is 500 million, 900 million to 400 million. So why is the expected profit, or what the insurance company is going to pay, or willing to charge 125 million? Come on, somebody. All right, what's the face value of the bond?
900 million.
Okay. And what's the expected value of the bond to the bondholder? What's that? 775. Okay, and the difference, 975?
125.
Okay. So, oops, I'm going the wrong way. Sorry, guys. So the difference between what this risk-neutral insurance company is willing to sell an insurance policy at and what he's willing to buy is, or the difference is 18.75 million. And that's basically the risk premium for the person. So this guy would definitely buy that policy. Okay. Here is another example, a graphical example of a bond. If I have a bond that has zero risk, in other words, the closest things are U.S. government bonds. If I have a bond that has zero risk, or investment has zero risk, those bonds are paying 8%. If I have a bond that has a standard deviation of 2% or 2, right? How much according to this graph would you have to pay me in interest for me to buy your bond?
4. But then it's the difference between 4 and 8.
That's the risk premium, you're right. But how much would you have to pay me in terms of interest? You're absolutely right what you said. Right there. Huh?
8%.
No, 8% is the risk-free rate. I'm saying that this is risky. If there's 2 standard deviations, right, how much do you have to pay me? What interest do you have to pay me? Go on, I don't know this. Try it. 12. 4. 8 plus 4 is 12. Right? And that's how much you have to pay me, right? For me to buy your bond, this risky bond that has standard deviation of 2. Okay, and that is the class for today, and we decided on the 10th of July, correct?
Yeah.
And
Homework 4 will be due. Yeah.
homework 4, we do the 3rd. Homework 3 is due tonight. Did you hear that, Julian?
Yes.
Okay, remember you have to get it. You have to get that to me by midnight, please. Eh?
If I don't have electricity, can I turn it into one?
Yes, yes, you may. I already said yes. You're gonna wash my truck. Again, a joke. But yeah, no problem.
So that's it for the class. So we completed that.
We are done. Yes.
No, but I mean, por lo que ya terminamos las clases del semestre, lo que queda es homework and the final, that's right.
Yes, we have done. We are done with the class because remember before the strike, we stayed later and we covered that extra material, and we got ahead by 1 second. We have one more lecture if not. Actually, I shouldn't say we have one more lecture. We wouldn't have finished lecture 13 today hadn't we done that.
Okay, so we don't have another lecture,
No more lectures, not in this class. Huh? Just the fun.
just the final. That's what I wanted to. Sí, ya necesito cáncer.
Okay, so I have two homeworks here, one from Jaime and one from Eric, right? Okay. That means Javier, you're gonna turn it in later by midnight?
Me too.
You're gonna turn it in, depending on whether you have power by midnight or tomorrow. Okay.
Today by midnight.
I'm sorry? Julian,
Midnight, I can send the pictures of the assignment to you.
can you guys hear what he said? I can barely hear what you're saying, Julian.
It's like freeze. I don't know why from here too. You hear me now?
Yeah, that's better. We can type on the chat.
Right, by cell phone. I call you. You can call me.
Okay, well, that's fine. I'm just gonna do it on the chat.
Okay.
Good night. Eric. Actually, can you stay a little bit? Okay.
Is it better now?
Yeah, actually, it is better now.
Okay. Yeah, that I was going to tell you that I can send you photos of the assignment today by midnight.
Okay, perfect. As long as, okay, that's fine. As long as you send it by midnight.
You said that the final is going to be, what was the date?
The final
Yeah,
is going to be on July 10th.
July 10th. And in my case, is it going to be the same format? Like you send it to me and I send you pictures?
Correct.
All right. And the last assignment was for that day also, right?
Yes, the last assignment will be that day.
Okay. And also, do you have the grades for the second midterm?
Okay. So, all right. So that'll be, put it on your calendar. Don't forget.
All right. No problem.
Okay. Thanks.
And so do you have the grades of the second midterm?
I'm sorry, what was that?
The grades of the second midterm, do you have them with you or not yet?
I do. They're online.
Oh, they're online. All right.
Can you see that grade?
Oh, yeah, 93.
Okay, yes.
All right.
Okay.
So we'll keep communicating. So thank you.
You're welcome. Okay. Mhm. Mhm. All right.
Thank you.
You're welcome. What happened, Eric? Mm-hmm.
I know I studied a lot, pero había unos ejercicios que, for some reason or another, I got stuck on them, and I don't even know why. I found them so easy before I finished the test, and so easy after I learned the test. Pero ahora con la mezcla entre, I've been having personal problems with phone, so I think then una mezcla desde eso, estaba tired porque había llegado de Aguadilla.
What was the rate of tuition? It might be something, right?
I had it, was my first time, 89.
You know, I could do what I was doing before, and say that on the final, if you do well, I'll just drop the second test altogether and I'll give you a grade 25% off. The two tests, the final. So if you that is,
Yeah, I get it.
so if you do that, I can talk about that. And there's still a chance to get an A, not a good chance to get an A. And as long as you don't bomb as bad as you did, actually, you're fine. I don't think you're close enough to see it. I'm sorry. If you don't bomb, then
I don't think I'm gonna do badly on the final test. Like I said, I really had a personal problem.
then in that case, I think we assuming you do well.
Yeah.
I'll just talk about that. Okay. All right. Crap, I thought I